I hope you are all having a great day. We're looking here at evaluation of this specific integral, which is a type 1 improper integral, an excellent example of an integral that will demonstrate convergence. Because technically we're looking here at an area below the curve. The fact that we have a minus infinity deems it as a type 1 improper integral. If you were to graph this out in terms of just a rough representation, you're looking here from minus infinity up to this 1. Your function would look very much like that. You're looking at all of this potential area up to right here. But when you're looking at this specific function, and we can just call it f of x, when you're seeing limit as x approaches minus infinity, your function here would really approach 0, because the function is approaching all along this horizontal asymptote x-axis, which is y equals 0. Hence, we can say that we will have a convergence play out, but we will show you the convergence will play out very well in this specific example. Also, when you're looking here at this rational function, we can easily simplify it before we proceed. We're really looking at something like this. You can do common denominator and all of that, fractional flipping. When you do all of that, you'll have e to the 2x. Over here, you'll have e to the 2x plus 1. All of that becomes your new rational function, which simplification algebra yields you all of that. And now what we do is we place it right over here on the top for our evaluation. We're looking here at e to the 2x over e to the 2x plus 1 dx. That right there is my function for evaluation. Now for this specific function, because we have that minus infinity, the lower limit, we can bring in a limit, and the limit can look something like this. Limit as t approaches minus infinity. And you can rewrite that entire integral, and it's not hard. You're looking here as this t1. We have e to the 2x over e to the 2x plus 1 dx. In this specific question, for this improper integral, I will employ a good and very relevant shortcut, and you'll see that come into play. We can do a polynomial substitution. You can take that denominator, make it e to the 2x plus 1 is equal to u. And then you know you have du is equal to 2e to the 2x dx. And dx is equal to du over 2e to the 2x. We can develop new intervals based on everything right over here. We have a t and a 1. It'll come here in places of x. u1 will become e to the 2t plus 1. u2, 1 will come here, be e squared plus 1. Now let me show you a shortcut looking right here at u1. We know we're looking here at limit as t approaches minus infinity. We have here, with regards to this interval limit, e to the 2t plus 1. This is no different than you just evaluating a function which looks like this. When you do this evaluation with regards to the limit, you're really looking at e to the minus infinity plus 1. This zeroes out, you're really looking at a 1. You can apply this entire limit procedure right here to your interval, and all of that interval ends up simplifying to just a simple 1. u1 will become just a single 1. And you can bring that into your entire improper integral and eliminate the entire limit procedures. Your entire integral becomes this. The lower limit has become a 1. Your upper limit is e squared plus 1. You have to bring in the items of this polynomial substitution. You have e to the 2x. Here you have a du over e to the 2x. And then you have a 2 because it was 2e to the 2x, and then you have a u representing all of this here. When you clean that out, cancel things out, this cancels out, you have a 1 over 2 come about. You have this remaining now. You have an integral with a lower limit 1, you have a e squared plus 1. And then you have a du over u. And you know you're looking here at a natural log of a u with upper limit e squared plus 1 and lower limit 1. You will do the difference of the two. You'll have natural log e squared plus 1 minus natural log of 1. This natural log of 1 is a 0, so you're really looking at just this. When you do this evaluation, you're getting a natural log e squared plus 1 over 2, and that right there is the end result. Your definite integral procedure for this type 1 improper integral is completed. You can bring out the calculator and solve it. You have e squared plus 1. You natural log it, you divide it by 2, you get 1.6346. Your area below the curve for that graph I showed you is 1.06346, a very finite area representing a good convergence for this type 1 improper integral right over here. Remember, the most crucial and the time saving step was this right over here, where on the limit interval I applied the limit calculation and I converted it into a 1. My limit changed to a 1 from this expression into 1. Otherwise, that expression would have carried along with its limit through all of this, and it would have been confusing. We could have still solved it, but applying the limit application to the interval limit saved us a lot of time and made everything easy. I'm confident this answer is good and this expression is good. And that right there brings us to the end of this type 1 improper integral evaluation video. Thank you for watching. Have a nice day.